Okay, class, let's review what we did yesterday and keep her moving on what we're gonna do today. So we talked about the chapters 1, right? We went over formula 1, 1, 2, 1, 3. Force is equal to mass times acceleration. Weight is equal to mass times gravity. The units on that are newtons, assuming that your acceleration is meters per second squared, gravity, and your mass is in kilograms. Then we kind of went into some unit conversions and talked about energy. We also, importantly though, before that, we defined the first and second law of thermodynamics, where the first law is an expression of the conservation of energy, meaning that energy in is equal to energy out, or energy in minus energy out is equal to the change in energy. And the second law of thermodynamics asserts that those have quantities, as well as energy favors lower quality. Energy will be transferred to lower quality systems. So in the example of a cup of coffee that's hotter than its surroundings, the heat, the high quality energy, the coffee, yum, hot, good, will transfer to the cold environment slowly over time. Then we talked about dimensions and how they're important. What I think was worth remembering is that the authors kind of touch base on how that SI unit is simple, but the English system is not, when it puts a burden on American engineers, which is why we're better than engineers in anywhere else around the world. USA. And we did a couple example problems and talked about unity conversion ratios. Dog-eared that. Still don't have my tabs. Shame on me. We talked about control volumes. Pretty standard stuff. Properties of a system. Density and gravity. Specific gravity. I think state and equilibrium, the state postulate. I think this is where we left off. Specific weight. The weight of a unit volume of a substance is called specific weight. State and equilibrium. Consider a system not undergoing any change. At this point, all properties can be measured or calculated to the entire system, which gives a set of properties and completely describes the condition or state of the system. At a given state, all the properties of a system have fixed values. If the value of even one property changes, the state will change to a different one. Figure 1-26 is a system. A system is shown at two different states. So we got, a similar piston setup where the difference is the volume. This one has a larger volume than this one. Thermodynamics deals with equilibrium states. The word equilibrium implies a state of balance. In an equilibrium state, there are no unbalanced potentials or driving forces within the system. A system in equilibrium experiences no changes when it is isolated from its surroundings. There are many types of equilibrium, and a system is not in thermodynamic equilibrium unless the conditions of all the relevant types of equilibrium are satisfied. For example, a system is in thermal equilibrium if the temperature is the same throughout the entire system, as shown in figure 1-27. So initially, the system is not at equilibrium because the temperature is not the same within its boundaries. or within the system. And then it approaches and becomes to be thermal equilibrium. That is, the system involves no temperature differential, which is the driving force for heat flow. Mechanical equilibrium is related to pressure, and a system is in mechanical equilibrium if there is no change in pressure at any point of the system with time. However, the pressure may vary within the system if the elevation... If there is no change in pressure at any point of the system with time. However, the pressure may vary within the system with elevation as a result of gravitational effects. Gotcha. So, if we took our system to the mountain, our pressure might change. For example, the higher pressure at a bottom layer is balanced by the extra weight it must carry, and therefore there is no imbalance of forces. The variation of pressure as a result of gravity in most thermodynamic systems is relatively small and usually disregarded. If a system involves two phases, it is in phase equilibrium, when the mass of each phase reaches an equilibrium level and stays there. Finally, a system is in chemical equilibrium if its chemical composition does not change with time. That is, no chemical reactions occur. A system will not be in equilibrium unless all the relevant equilibrium criteria are satisfied. Okay. So that's equilibrium. The state postulate. As noted, the state of a system is described by its properties, but we know from experience that we do not need to specify all properties in order to fix a state. Once a sufficient number of properties are specified, the rest of the properties assume certain values automatically. That is, specifying a certain number of properties is sufficient to fix a state. The number of properties required to fix the state of a system is given by the state postulate. The state of a simple compressible system is completely specified by two independent intensive properties. So that's the state postulate. The state of a simple compressible system is completely specified by two independent intensive properties. So this is PV equals nRT. So once two independent intensive properties, and intensive properties do not rely on mass. So intensive properties are temperature, pressure. Let's review. It's here somewhere. Did I go too far? Yes, I did. Temperature, pressure, density, volume, mass? Temperature, pressure, density. Intensive properties. Independent of a mass of the system. So temperature, pressure, and density. The state of a simple compressible system is completely specified when two, either temperature, pressure, or density, two of the intensive properties are specified. All right. A system is called a simple compressible system in the absence of electrical, magnetic, gravitational motion, and surface tension effects. These effects are due to external force fields and are negligible for most engineering problems. Otherwise, an additional property needs to be specified for each effect that is significant. If gravitational effects are to be considered, for example, the elevation z needs to be specified in addition to two properties necessary to fix the state. The state postulate that two properties specified be independent to fix the state. Two properties are independent if one property can be varied while the other is held constant. Temperature and specific volume, for example, are always independent properties, and together they fix the state of a simple compressible system. Temperature and pressure, however, are independent properties for single-phase systems, but are dependent properties for multi-phase systems. At sea level, water boils at 100 degrees Celsius, but on a mountaintop where the pressure is lower, water boils at a lower temperature. That is, T is a function of pressure during a phase change process. Thus, temperature and pressure are not sufficient to fix the state of a two-phase system. Phase change processes are discussed in detail in Chapter 3. State postulate requires two properties specified be independent to fix the state. So in a two-system, or in a multi-phase system, temperature and pressure cannot, or are not independent. Therefore, they cannot satisfy the state postulate, being a simple compressible system specified by two independent intensive properties. So density would need to be constant in a two-system that doesn't make sense though, because density of water and density of the gas where the water be boiled into would be different. So therefore, that's not a simple compressible system. So therefore, we need to go into more detail in Chapter 3. Sounds like a plan. Let's get to it. Any change that a system undergoes from one equilibrium state to another is called a process. And the series of states through which a system passes during a process is called the path of the process. To describe a process completely, one should specify the initial and final states of the process, as well as the path it follows and the interactions with the surroundings. So, according to this graph, the process starts at state 1. The process follows this curved path, and it interacts with, as property B increases, property A also increases, to finally get us to the end of the process, state 2. When a process speeds in such a manner that the system remains infinitesimally close to an equilibrium state at all times, it is called quasi-static or quasi-equilibrium process. A quasi-equilibrium process can be viewed as a sufficiently slow process that allows the system to adjust itself internally so the properties in one part of the system do not change any faster than those at the other parts. So here's an example, illustrated in figure 1-30. A slow compression quasi-equilibrium versus a very fast compression. So when a gas in a piston cylinder device is compressed suddenly, the molecules near the face of the piston will not have enough time to escape, and they will pile up in a small region in the front of the piston. So there's a pile up of molecules, thus creating a high pressure region there. Because of this pressure difference, the system can no longer be said to be in equilibrium. And this makes the entire process non-quasi-equilibrium. So let's call this P equals 3, and this is P equals 1. Whereas this is P equals 1.2, P equals 1.2, approximately. That's what that means. However, if the piston is moved slowly, the molecules have sufficient time to redistribute, and there will not be a molecule pile up in front of the piston. As a result, the pressure inside the cylinder will always be nearly uniform and will rise at the same rate at all locations. Since equilibrium is maintained at all times, this is a quasi-equilibrium process. It should be pointed out that quasi-equilibrium process is an idealized process that is not a true representation of an actual process, but many actual processes closely approximate it, and they can be modeled as quasi-equilibrium with negligible error. Engineers are interested in quasi-equilibrium processes for two reasons. First, they are easy to analyze. Second, work-producing devices deliver the most work when they operate on quasi-equilibrium processes. Therefore, quasi-equilibrium processes serve as standards to which actual processes can be compared. Process diagrams plotted by employing thermodynamic properties as coordinates are very useful in visualizing the processes. Some common properties that are used as coordinates are temperature, pressure, volume, or specific volume. And figure 131 shows the pressure volume diagram of a compression process of a gas. So we got state 1, we got state 2. Initially the volume is very large, but the pressure is very small. And there's a process where the piston gets pushed, the volume decreases, the pressure increases, and here's the path that it takes to get there. So although this may be happening as a quasi-equilibrium process where the pressure here is greater than the pressure here during the action, or along the path, for sake of ease of analysis, the final state assumes that this is a constant pressure, I think. Process diagrams are plotted by employing thermodynamics. Note that the process path indicates a series of equilibrium states through which the system passes during a process and has significance for quasi-equilibrium processes only. For non-quasi-equilibrium processes, we cannot characterize the entire system by a single state. Ooh, okay. And thus, we cannot speak of a process path for a system as a whole. A non-quasi-equilibrium process is denoted by a dashed line between the initial and final states instead of a solid line. So this is quasi. Non-quasi would be using a dotted line. The prefix ISO is often used to designate a process for which a particular property remains constant. An isothermal process, for example, is a process where temperature remains constant. An isobaric process is a process during which the pressure remains constant. An isochoric or isometric process is a process in which the specific volume remains constant. A system is said to have undergone a cycle if it returns to its initial state at the end of a process. That is, for a cycle, the initial and final states are identical. So think back to PChem, think back to the Carnot cycle, where I'm pretty sure, that's an engine, I want to say it's pressure, volume, bing, bang, bing, boom. We're doing one of these, something like that. And we got 1, 2, 3, 4. They go into this example in further detail. The terms steady and uniform. Steady. Alright, let's break time. 20 minutes in. Let's review. First, we went over a review and we talked about state and equilibrium, as well as the state postulate and processes and cycles. Get some water, stay hydrated. Stretch the legs. Make it quick. The steady flow process. The terms steady and uniform are often in engineering, and thus it is important to have a clear understanding of their meanings. The term steady implies no change with time. The opposite of steady is unsteady or transient. The term uniform, however, implies no change with location over a specified region. These meanings are consistent with their everyday use. Steady girlfriend, uniform properties. What the... A large number of engineering devices operate for long periods of time under the same conditions, and they are classified as steady flow devices. Processes involving such devices can be represented reasonably well by a somewhat idealized process called the steady flow process, which can be defined as a process during which a fluid flows through a control volume steadily. Steady state a process. That is, the fluid properties can change from point to point within the control volume, but at any fixed point they remain the same during the entire process. Therefore, the volume, the mass, and the total energy content E of the control volume remains constant during a steady flow process. Steady flow conditions can be closely approximated by devices that are intended for continuous operation, such as turbines, pumps, boilers, condensers, heat exchangers, or power plants, or refrigeration systems. Some cyclic devices, such as reciprocating engines or compressors, do not satisfy any of the conditions stated above, since the flow at the inlets and the exits will be pulsating and not steady. However, the fluid properties vary with time in a periodic manner, and the flow through these devices can still be analyzed as a steady flow process by using time-averaged values for the properties. Interesting. So we got a figure here. We got mass in, we got mass out. This is the control volume. The temperature changes. We got mass in, we got mass out. This is the control volume. The temperature changes. During a steady flow process, fluid properties within the control volume may change with position, but not with time. Okay. Temperature and the zeroth law of thermodynamics. Although we are familiar with temperature as a measure of hotness or coldness, it is not easy to give an exact definition for it. Based on our physiological sensations, we express the level of temperature qualitatively with words like freezing cold, cold, warm, hot, and red hot. However, we cannot assign numerical values to temperatures based on our sensations alone. Furthermore, our senses may be misleading. A metal chair, for example, will feel much colder than a wooden one, even when both are the same temperature. Fortunately, several properties of materials change with temperature in a repeatable and predictable way, and this forms the basis for accurate temperature measurement. The commonly used mercury in glass thermometer, for example, is based on the expansion of mercury with temperature. Temperature is also measured by using several other temperature-dependent properties. It is a common experience that a cup of hot coffee left on the table eventually cools off and a cold drink eventually warms up. That is, when a body is brought into contact with another body that is at a different temperature, heat is transferred from the body at a higher temperature to the one at lower temperature until both bodies attain the same temperature. At that point, the heat transfer stops, and the two bodies are said to have reached thermal equilibrium. The equality of temperature is the only requirement for thermal equilibrium. The zeroth law of thermodynamics states that if two bodies are in thermal equilibrium with a third body, they are also in equilibrium with each other. It may seem silly that such an obvious fact is called one of the basic laws of thermodynamics. However, it cannot be concluded from the other laws of thermodynamics, and it serves as a basis for the validity of temperature measurement. By replacing the third body with a thermometer, the zeroth law can be restated as two bodies are in thermal equilibrium if both have the same temperature reading, even if they are not in contact. The zeroth law was first formulated and labeled by R.H. Fowler in 1931. Wonder if he was a bird hunter. As the name suggests, it's a fundamental physical property. Its as the name suggests. Its value as a fundamental physical principle was recognized more than half a century after the formulation of the first and second law of thermodynamics. It was named the 0th law because it should have preceded the first and second laws of thermodynamics. Neat. Temperature scales, that's worth highlighting. The 0th law of thermodynamics. So the impact of the 0th law of thermodynamics is that we can trust thermometers. But it wasn't published until 1931, which is a head scratcher. Temperature scales enable us to use a common basis for temperature measurements, and several have been introduced throughout history. All temperature scales are based on some easily reproducible states, such as the freezing point of water. Yes, freezing and boiling points of water, which are also called the ice point and the steam point, respectively. A mixture of ice and water that is in equilibrium with air saturated with vapor at 1 atmosphere pressure is said to be at ice point, and a mixture of liquid and water vapor with no air is in equilibrium at 1 atmosphere pressure is said to be at the steam point. The temperature scales used in SI units, SI and English system today are the Celsius scale, formerly called centigrade, and the Fahrenheit scale. On the Celsius scale, the ice and steam points were originally assigned to values 0 and 100 degrees Celsius, respectively. The corresponding values on the Fahrenheit scale are 32 and 212 degrees Fahrenheit. These are often referred to as 2-point scales, since temperature values are assigned at 2 different points. In thermodynamics, it is very desirable to have a temperature scale that is independent of the properties of any substance or substances. Such a temperature scale is called a thermodynamic temperature scale, which is developed later in conjunction with the second law of thermodynamics. The thermodynamic temperature scale in the SI is the Kelvin scale, named after Lord Kelvin. The temperature unit on this scale is the Kelvin, which is designated by K. The lowest temperature on the Kelvin scale is absolute 0, or 0K. Then it follows that only one non-zero reference point needs to be assigned to establish the slope of this linear scale. Using non-conventional refrigeration techniques, scientists have approached absolute 0 Kelvin. They achieved 0.000000002 Kelvin in 1989 by using unconventional refrigeration techniques. Wonder what they did. The thermodynamic temperature scale in the English system is the Rankine scale, named after William Rankine. Temperature unit on this scale is the Rankine, which is designated by R. The temperature scale that turns out to be nearly identical to the Kelvin scale is the ideal gas temperature scale. The temperature on this scale are measured using a constant volume gas thermometer, which is basically a rigid vessel filled with a gas, usually hydrogen or helium, at low pressure. This thermometer is based that at low pressures, the temperature of a gas is proportional to its pressure at constant volume. That is, the temperature of a gas or of fixed volume varies linearly with the pressure at sufficiently low pressures. then the relationship between the temperature and pressures of the gas in the vessel can be expressed as T is equal to A plus B times P, a linear relationship, equation 1A, where the values of constants A and B for a gas thermometer are determined experimentally. Once A and B are known, the temperature of a medium can be calculated from this relation by immersing the rigid vessel of gas thermometer into a medium and measuring the gas pressure when the thermal equilibrium is established between the medium and the gas vessel, whose volume is held constant. An ideal gas temperature scale can be developed by measuring the pressures of the gas in the vessel are at two reproducible points, such as the ice and steam points, and assigning suitable values to temperatures at those points. Considering that only one straight line passes through two fixed points on the plane, these two measurements are sufficient to determine the constants A and B in equation 1-8. Then the unknown temperature T of a medium corresponding to a pressure reading P can be determined from that equation by a simple calculation. The value of the constants will be different for each thermometer depending on the type and the amount of gas in the vessel, and the temperature values assigned at the two reference points. If the ice and steam points are assigned the values 0 degrees C and 100 degrees C respectively, then the gas temperature scale will be identical to the Celsius scale. In this case, the values of the constant A, which corresponds to an absolute pressure of 0, is determined to be negative 273.15 degrees Celsius, regardless of the type and amount of gas in the vessel of the gas thermometer. That is, on a pressure temperature diagram, all the straight lines passing through the data points in this case will intersect the temperature axis at negative 273.15 degrees Celsius when extrapolated. As shown in figure 1-35, this is the lowest temperature that can be obtained by a gas thermometer, and thus we can obtain an absolute gas temperature scale by assigning a value of 0 to the constant A in equation 1.8. In that case, equation 1.8 reduces to T is equal to B times P, and thus we need to specify the temperature only at one point to define an absolute gas temperature scale. It should be noted that the absolute gas temperature scale is not a thermodynamic temperature scale, since it cannot be used at very low temperatures due to condensation and at very high temperatures due to dissociation and ionization. However, absolute gas temperature is identical to thermodynamic temperature in the temperature range in which the gas thermometer can be used. Thus, we can view thermodynamic temperature scale at this point as an absolute gas temperature scale that utilizes an ideal or imaginary gas that always acts at low pressure, that acts as a low pressure gas regardless of the temperature. If such a gas thermometer exists, it would read 0 Kelvin at absolute 0 pressure, which corresponds to negative 273.15 degrees Celsius on the Celsius scale. The Kelvin scale is related to the Celsius scale by Kelvin is equal to Celsius plus 273.15. The Rankine scale is related to the Fahrenheit scale by Rankine is equal to Fahrenheit plus 459.67. It is common practice to round the constant in equation 1.9 to 273 and 1.10 to 460. Temperature unit or temperature scales in the two-unit system are related by Rankine is equal to 1.8 Kelvin and Fahrenheit is equal to 1.8 Celsius plus 32. A comparison of various temperature scales is given in figure 137. The reference temperature chosen on the Kelvin scale was 273 or 0 degrees Celsius, which is the temperature at which water freezes or ice melts, and water exists as a solid-liquid mixture in equilibrium under standard atmospheric pressures, the ice point. At the 10th General Conference on Weights and Measures in 1954, the reference point was changed to a much more precisely reproducible point, the triple point of water, the state at which all three phases of water coexist in equilibrium, which was assigned to the value of 273.16 K. The Celsius scale was also redefined at this conference in terms of the ideal gas temperature and a single fixed point, which is again the triple point of water, and assigned value of 0.01 degrees Celsius. The boiling temperature of water, the steam point, was experimentally determined to be again 100 degrees Celsius. And thus the new and old Celsius scales were in good agreement. So let's look at this graph. We got gas A, B, C, D, extrapolation, -273, measured data points, pressure, P versus T plot of experimental data obtained from a constant volume gas thermometer using 4 different gases, but at different but low pressures. Nice. And we got no pressure at so this is our unconventional. Just pull a real low vacuum and measure the temperature. Absolute vacuum equals no pressure. Which, like, if you think about how temperature is generated by interactions with molecules as they collide with the walls and each other, that creates temperature. More interactions equals more temperature. No interactions equals no temperature. Hot dog, that was 20 minutes. Jesus. Who knew the zeroth law of thermodynamics could be so in depth, and the relationships between temperature were so important or so fundamental. But I think it's worth writing down these formulas. 1, 9, 1, 10, 1, 11, 1, 12. So K is equal to T degrees C plus 273.15. TR is equal to T degrees F plus 459.67. TR is equal to 1.8 TK, and then TF is equal to 1.8 T degrees C plus 32. Alright, stretch the legs, get the blood flowing, get it pumping. 2 minutes, drink some water. Okay, great. International Temperature Scale of 1990. The International Temperature Scale of 1990, which supersedes the International Practical Temperature Scale of 1968, 1948, and 1927, was adopted by the International Committee of Weights and Measures at its meeting in 1989 at the request of the 18th General Council Conference on Weights and Measures. The ITS 90 is similar to its predecessors except that it is more refined with updated values of fixed temperatures, has an extended range, and conforms more closely to the thermodynamic temperature scale. On this scale, the unit of thermodynamic temperature is again the Kelvin, defined as the fraction 1 over 273.16, the thermodynamic temperature of the triple point of water, which is the sole defining fixed point of the ITS 90 and the Kelvin scale. It is most important thermometric fixed point used in the calibration of thermometers to ITS 90. The unit of Celsius is the temperature. The unit of Celsius temperature is the degree Celsius, which is defined by, or which is by definition equal in magnitude to the Kelvin. A temperature difference may be expressed in kelvins or degrees Celsius. The ice point remains the same at 0 degrees Celsius, 273.15 Kelvin, in both ITS 90 and ITPS-68. But the steam point is 99.975 C degrees Celsius in ITS 90 with an uncertainty of plus or minus 0.005 degrees Celsius. Whereas it was 100 degrees Celsius in IPTS-68. The change is due to the precise measurements made by gas thermometry by paying particular attention to the effect of sorption, the impurities in a gas absorbed by the walls of the bulb at the reference temperature being desorbed at higher temperatures, causing the measured gas pressure to increase. The ITS 90 extends upward from 0.65 K to the highest temperature practically measurable in terms of the Planck radiation law using monochromatic radiation. It is based on specifying definite temperature values on a number of fixed and easily reproducible points to serve as benchmarks and expressing the variation of temperature in a number of ranges and sub-ranges in functional form. In ITS 90, the temperature scale is considered in 4 ranges. The ranges from 0.65 to 5 Kelvin. The temperature scale is defined in terms of the vapor pressure relations for helium-3 and helium-4. Between 3 and 24.5561 Kelvin, the triple point of neon, it is defined by means of a properly calibrated helium gas thermometer. From 13.8033 Kelvin, the triple point of hydrogen, to 1234.93 Kelvin, the freezing point of silver, it is defined by means of platinum resistance thermometers calibrated at specific sets of defining fixed points. Above 1234.93 Kelvin is defined in terms of the Planck radiation law and a suitable defining fixed point, such as the freezing point of gold, 1337.33 Kelvin. We emphasize the magnitudes of each division of 1 Kelvin and 1 degree Celsius are identical. Therefore, when we are dealing with temperature differences delta T, the temperature interval on both scales is the same. Raising the temperature of a substance by 10 degrees Celsius is the same as raising it by 10 degrees Kelvin. So delta T in units of Kelvin is equal to delta T in units of Celsius. I'm sure y'all probably knew that already, but now you know how at the International Temperature Scale and the International Practical Temperature Scale of 1990 and 1968 respectively defined the ranges and the method used for defining each range to determine a temperature scale. Kind of interesting. History, man, history. It comes and goes. And here it is, sitting in a book. Some thermodynamics that we have to learn. Some thermodynamics, edit that part out. I really like this. Leave that in though. Some thermodynamic relations involve the temperature, and often question arises whether it is in Kelvin or Celsius. If the relation involves temperature differences, such as A equals B delta T, it makes no difference and either can be used. However, if the relation involves temperatures only instead of temperature differences, such as A is equal to B times T, then K must be used. When in doubt, it is always safe to use K because there are virtually no situations in which the use of K is incorrect. But there are many thermodynamic relations that will yield an erroneous result if degree C is used. Nice. Oh, nice. Humans are most comfortable when the temperature is between 65 degrees Fahrenheit and 75 degrees Fahrenheit. Express these temperatures limits in degrees C. Convert the size of this temperature range, 10 degrees Fahrenheit, to Kelvin, C, and Rankine. Is there any difference in the size of this range as measured in relative or absolute units? So what are we doing? We're using our formulas. Convert the size of this range, 10, alright. So 10 degrees F is equal to, well, let's go EX 1-4. 10 degrees F is equal to 1.8 times T degrees C plus 32. Hmm. 22 divided by 18 is... Let's just do it. 12.2, repeating. Degrees C. That don't make sense. but maybe it do. Why not? Yeah, it does. 0 degrees C is 32, so. And now oof. Fundamental mistake. Temperature differential in Fahrenheit does not equal temperature differential in Celsius. There we go. Be careful when making temperature unit conversions. First, identify whether the conversion involves a temperature value or a temperature value change. See, I wasn't careful and I made a mistake. but that's why that's in here. Good practice. Pressure is defined as a normal force exerted by a fluid per unit area. Normally, we speak of pressure when we deal with a gas or liquid. The counterpart of pressure in solids is normal stress. However, that pressure is a scalar quantity, while stress is a tensor. Since pressure is defined as force per unit area, it has the same unit of newtons per square meter, which is called a Pascal. That is, 1 Pascal is equal to 1 Newton per meter squared. Oh, buddy. The pressure unit Pascal is too small for most pressures encountered in practice. Therefore, its multiples kilopascal, 1 kPa is equal to 10 to the third Pa, and megapascal are commonly used. 3 other pressure units commonly used in practice, especially in Europe, are bar, atmosphere, and kilogram force per square centimeter. Here are their unit conversions. Note, the pressure units bar, atmosphere, and kilogram force per centimeter squared are almost equivalent to each other. In the English system, the pressure unit is pound force per square inch, or psi, and 1 atmosphere is equal to 14.696 psi. The pressure units kilogram force per centimeter squared and pound force per inch squared are also denoted by kilogram per centimeter squared and pound per inch squared, respectively, and they are commonly used in tire gauges. It can be shown that 1 kilogram force per centimeter squared is equal to 14.223 psi. Pressure is also used on solid surfaces as synonymous with normal stress, which is the force acting perpendicular to the surface per unit area. For example, a 70 kilogram person with a total foot imprint of 280 square centimeters exerts a pressure of 70 kilogram force per 280 square centimeters, which is 0.25 kilogram force per centimeter squared on the floor. If the person stands on 1 foot, the pressure doubles. If the person gains excessive weight, or he or she is likely to encounter foot discomfort because of the increased pressure on the foot. The size of the bottom of the foot does not change with weight gain. This also explains how a person can walk on fresh snow without sinking by wearing large snowshoes, and how a person cuts with little effort when using a sharp knife. The actual pressure at a given position is called absolute pressure, and it is measured relative to absolute vacuum, i.e., absolute zero pressure. Most pressure measuring devices, however, are calibrated to read 0 in the atmosphere, and so they indicate the difference between the absolute pressure and the local atmospheric pressure. This difference is called gauge pressure. P gauge can be positive or negative, but pressures below atmospheric pressures are sometimes called vacuum pressures and are measured by vacuum gauges that indicate the difference between the atmospheric pressure and the absolute pressure. Absolute gauge and absolute pressures are related to each other by P gauge is equal to P abs minus P atmosphere, and vacuum pressure is equal to P atmosphere minus P absolute. This is illustrated in figure 1-41. So we have P atmosphere, less than atmosphere is a vacuum. So vacuum is equal to atmosphere minus absolute. And then we got atmosphere. Our gauge is greater than atmosphere. And then we got absolute. So P gauge is equal to P apps minus P ATM. Like other pressure gauges, the gauge used to measure the air pressure in an automobile tire reads the gauge pressure. Therefore, the common reading of 32 psi indicates a pressure of 32 psi above the atmospheric pressure. At a location where the atmospheric pressure is 14.3 psi, for example, the absolute pressure in the tire is 32 plus 14.3, which is equal to 46.3 psi. In thermodynamic relations and tables, absolute pressure is almost always used. Throughout this text, the pressure will denote absolute pressure unless specified otherwise. Often letters A for absolute pressure and G for gauge pressure are added to pressure units such as PSIA and PSIG to clarify what is meant. We got another example problem. Oh, buddy, yes, my favorite part. Okay. A vacuum gauge connected to a chamber reads 40 kilopascals at a location where the atmospheric pressure is 100 kilopascals. Determine the absolute pressure in the chamber. Nice. So, without looking at the solution, a vacuum gauge. So, Pvac equals to 40. PATM equals to 100. kPa, kPa. So 40 equals 100 minus P abs plus P abs minus 40 P absolute is equal to 60 kPa. Ding ding ding. Note the local value of atmospheric pressure is used when determining the absolute pressure. Variation of pressure with depth. It will come as no surprise to you that pressure in a fluid at rest does not change in horizontal direction. This can be shown easily by considering a thin horizontal layer of fluid and doing a force balance in any horizontal direction. However, This is not the case in the vertical direction in a gravity field. Pressure in a fluid increases with depth because more fluid rests on deeper layers, and the effect of this extra weight on a deeper layer is balanced by an increase in pressure. To obtain the relation for the variation of pressure with depth, consider a rectangular fluid element with a height delta z, length delta x, and depth delta y equals 1 into the page in equilibrium as shown in figure 1-43, assuming the density of the fluid rho to be constant. A force balance in the vertical z direction gives so the sum of the forces in the z direction is equal to mass mass times the acceleration in the z direction, which is equal to 0, which is defined by buoyancy pressure times delta x times delta y into the page minus P2 weight pressure times delta x times delta y minus density times gravity times the size of the body is equal to 0, where W, weight, is equal to mass times gravity is equal to density times gravity times volume is the weight of the fluid element, and delta Z is Z2 minus Z1. Dividing by X and Y, rearranging gives the change in pressure is equal to P2 minus P1, which is equal to the opposite of density times gravity times delta Z, which is equal to specific weight of the fluid times delta Z. Thus, we conclude that pressure difference between 2 points in a constant density fluid is proportional to the vertical distance delta Z between the 2 points and density of the fluid. This is just like fluid mechanics, where we learned that using the Bernoulli equation, we could figure the velocity based off of delta Z of v of this stream. We could figure the velocity of this stream once we know the specific weight or the density of our fluid and the height between and the height between the hole that we shot in the tank and the top of the liquid. Noting the negative sign, pressure in a static fluid increases linearly with depth. This is what a diver experiences when diving deeper in a lake. An easier equation to remember and apply between any 2 points in the same fluid under hydrostatic conditions is P below is equal to P above plus rho G delta Z, which is equal to P above plus specific weight times delta Z, the absolute value of delta Z, where below refers to the point at lower elevation, deeper in the fluid, and above refers to the point at higher elevation. If you use this equation consistently, you should avoid sign errors. For a given fluid, the vertical distance delta z is sometimes used as a measure of pressure and is called the pressure head. We also conclude from equation 1-17 that for small to moderate distances, the variation of pressure with height is negligible for gases because of their low density. The pressure in a tank containing a gas, for example, can be considered to be uniform since the weight of the gas is too small to make a significant difference. Also, the pressure in a room filled with air can be approximated as a constant. If we take the above point to be at the free surface of a liquid open to the atmosphere, where the pressure is atmospheric pressure, then equation 118, the pressure at a depth h below the free surface becomes P equals P ATM plus rho GH, or P gauge is equal to rho GH, where H is the height between your gauge and the surface of the liquid. Liquids are essentially incompressible substances, and thus the variation of density with depth is negligible. This is also the case for gases when elevation change is not very large. The variation of density of liquids or gases with temperature can be significant, however, and may need to be considered when high accuracy is desired. Also, at great depths, such as those encountered in oceans, the change in density of a liquid can be significant because of the compression by the tremendous amount of liquid weight above. The gravitational acceleration g varies from 9.807 meters per second squared at sea level to 9.764 meters per second squared at elevation of 14,000 meters where large passenger planes cruise. This is a change of just 0.4% in the extreme case, therefore g can be approximated as a constant with negligible error. For fluids with density changes significantly with elevation, a relation for the variation of pressure with elevation can be obtained by dividing equation 117 by delta z and taking the limit as delta z approaches 0. This yields change in pressure over change in height is equal to the opposite of density times gravity. Note that change in pressure is negative when change in pressure or height is positive, since pressure decreases in an upward direction when the variation of density with elevation is known. The pressure difference between any 2 points, 1 and 2, can be determined by integration to be change in pressure is equal to pressure 2 minus pressure 1, which is equal to the opposite of 2 to 1 rho g delta z, change in height. For constant density and constant gravitational acceleration, this relation reduces to equation 1-17 as expected. Under alright. Pressure in a fluid at rest is independent of the shape or cross-section of the container. It changes with the vertical distance but remains constant in other directions. However, the pressure is the same at all points on a horizontal plane in a given fluid. The Dutch mathematician Simon Stevin published in 1586 the principle related in figure 1-46. Note the pressures at points A, B, C, D, E, F, and G are all the same since they are at the same depth, and they are interconnected by the same static fluid. However, the pressures at point H and I are not the same, since these 2 points cannot be interconnected by the same fluid. An example, we cannot draw a curve from point I to point H while remaining in the same fluid all the times. Although they are at the same depth, can you tell at which point the pressure is higher? Also, notice that the pressure force exerted by the fluid is always normal to the surface at the specified points. A consequence of the pressure in a fluid remaining constant in a horizontal direction is that the pressure applied to a confined fluid increases the pressure throughout by the same amount. This is called Pascal's law. After Blaise Pascal, Pascal also knew that the force applied by a fluid is proportional to the surface area. He realized that two hydraulic cylinders of different areas could be connected, and the larger could be used to exert a proportionally greater force that applied to the smaller Pascal's machine. To the smaller. Pascal's machine has been the source of many inventions that are a part of our daily lives, such as hydraulic brakes and lifts. This is what enables us to lift a car easily with one arm, as shown in figure 147, noting that P1 equals to P2 since both pistons are the same level. The effect of small height differences is negligible, especially at high pressures. The ratio of output force to input force is determined to be P1 is equal to P2, which is the F1 over A1 equals F2 over A2. To be the area ratio, A2 over A1 is called the ideal mechanical advantage of the hydraulic lift. Using a hydraulic car jack with a piston area ratio of A2 over A1 is equal to 100, for example, a person can lift a 1,000 kilogram car just by applying 10 kilograms force. So let's unpack figure 146. Simon Stephen, a mathematician. So we got, what are we looking at? Atmospheric pressure, water, with a varying degree of a bottom. And since A, B, C, D, E, F, and G are all on the same plane, they all have the same pressure. However, H and I are on a lower plane. They have a different pressure. And PA is equal to the atmospheric pressure plus the density of water times the gravitational acceleration constant times height. And here we got A1, P1 to A2, P2. So in a hydraulic jack, we can put 10 pounds force to here and get 1,000 kilogram force if A1 is 10 times smaller than A2, right? I think that's how I understand it. and we're going to call it there.